Good afternoon. I hope you can hear me. I have received the message about the recording and uploading of the lectures. All lectures are recorded and uploaded into the system that is called Virtuale, accessible from my website of the university. You remember that we had partially discussed the photodiode. We actually described the functioning in the so-called continuous mode, in which the switch S is always kept closed. And we calculated the current density, and the current density comes out to be the superposition of two contributions. One contribution comes from the photons, from the optical generations induced by the photons, and it is given by QGS over K. K is the absorption coefficient of the photons. And the other contribution to the current is due to the thermal generation, and it is given by Q times the intrinsic concentration over the generation lifetime times the length L of the depleted region. If there is enough illumination, which is typical of the standard operating conditions, and if the generation lifetime tau g is large enough, which is typical if the material is very good, that is, there are not so many defects in the material, the optical term is dominant, which means that we can neglect the thermal part, and in doing so, we eliminate the presence of L. L is the width of the space charge region of the PN junction, and as you remember, it depends on the applied voltage. So when we eliminate this term, the current does not depend anymore on the applied voltage. So it is a constant current that depends only on the amount of optical generation given by G sub S. On the other hand, when we have a constant current and we want to represent it in the equivalent circuit, we do it by using a current generator with a constant current. Another issue is that, as you can see in this formula, the current density has a negative sign. That means that the direction in which the current flows is opposite to the positive direction of the x-axis. So this explains why when we look at the equivalent circuit, the one on the right, of course, since we are for the moment considering the continuous mode of operation, we assume that the switch is closed, okay? So we have, if we multiply the current density due to the optical generation by the cross-sectional area of the device, we obtain a current associated to the optical generation. We call it IG. As I said before, it is represented by a current generator, and the orientation of this current is bottom up because it is opposite to the positive direction of the x-axis. In the continuous mode of operation, this current, of course, flows through the generator, through the switch, through to the bias generator, and through the resistance R. Okay, so since the actual flow of the current is clockwise, the current flows into the resistance bottom up. Okay, so the voltage drop that we measure across the resistance, whose name is VR, is negative. Okay. Now, this is a good sensor, but this voltage drop may be small. We want to improve it, okay? So we revert from the continuous mode of operation to the storage mode. In the storage mode, the switch S is alternatively kept closed and open. When we open the switch, no current can flow through the resistance R, so no current can flow on the loop that is on the right, okay? But the current generator keeps functioning because we have the illumination. So there is a current IG that flows across the capacitor, okay? Because the PN junction, when we bias it in the reverse condition, it is essentially a capacitor. So what happens in the capacitor? It happens that the charge initially stored in the capacitor, and of course this charge is initially some negative charge on the upper side of the capacitor, and this upper charge is due to the acceptor dopants on the P side of the junction. And on the other side, there is an equal and opposite charge that is positive due to the positive donor ions on the N side, okay? When we have a current IG that flows through the capacitor, this current essentially brings positive charges bottom up, which means that the total amount of positive charge on the lower electrode of the capacitor decreases. And similarly, the negative charge on the upper electrode of the capacitor also decreases, okay? So what happens to the voltage drop across the capacitor, that is the voltage between points alpha and beta in the figure? This voltage drop is called VD, okay? Initially, before we open the switch, obviously, VD is forced by V0. And V0 is negative. So initially, VD has some negative value forced by the application of the constant voltage V0 to the device. But during the integration time, since we are bringing positive charges from the lower electrode of the capacitor to the upper electrode, the modulus of VD decreases, okay, because we have less charge on each side of the capacitor. But VD is negative, so VD during the integration time becomes less negative, okay? Conclusion, after the integration time has finished, we have a value of the voltage drop across the capacitor that is some VD, still negative, but smaller in modulus than the original VD. Another observation is that during the integration time, the loop on the right is opened. So there is no possible current across resistance R during the integration time. For this reason, there is no voltage drop. So during the integration time, VR is equal to 0, so that the potential at point gamma and the potential at point beta are equal to each other. Okay? So beta has the same potential as gamma. Consider it to ground. Okay? Assume that gamma is grounded. Okay? It is not necessary, but just for simplicity. At the end of the integration period, we close the switch. So gamma is grounded, so gamma does not change. Alpha goes in 0 time to the value VD, and that value was the value reached by VD because of the integration. It goes from the value VD, that is negative but not very negative, to the value V0. And V0 is also negative but larger in modulus than VD. So point alpha in 0 time has the voltage at point alpha has a discontinuity. It becomes in 0 time more negative. Okay? You remember from elementary circuit theory that a capacitor does not allow for a discontinuity in the voltage, a time discontinuity in the voltage, okay? Because if it did, then the current crossing the capacitor would be infinite, okay? So it is forbidden for the voltage VD to change discontinuously. This means that the change in the voltage of alpha that becomes more negative reflects into an equal change in beta. So beta was originally equal to 0, the potential in beta, because there was no current flowing through the resistance R. So at the time when we close the switch, beta is the voltage at beta is 0. Then it becomes negative. Okay. Due to that, we have a peak of current through the resistance, because the resistance, 1 instant before closing the switch, has 0 voltage across it. 1 instant after has a negative voltage across it. So we have a large current flowing through the resistance. And this current produces a voltage drop, VR, that is of course negative, through the resistance. Okay? Now, what do we gain in the storage mode operation? What we gain is that the current flowing through the resistance when we close the switch is much, much larger than IG, than the current produced by the generator. So that the voltage VR produced at the time of closing the switch is also several times larger than IG. So the current through R at the time of closing the switch divided by the current of the generator, Ig, is called the gain of the storage mode. And this gain may be quite large, like 20, 30 times, okay? So this signal is much, much easier to detect than the signal that we would have in the continuous mode operation. What happens after we close the switch and we have the sudden peak of current in the resistance? It happens that the charges on the two plates of the capacitor must go back to the steady state value, so to the value that corresponds to a steady state condition in which the switch is closed and we apply V0, okay? So this is a transient that takes time, and we must wait until this transient has finished. Otherwise, the charge on the two plates of the capacitor has not reached the steady state value, and if we start another integration period too early, and then we shall find some charge due to the previous integration in the new integration. So the successive reading of the device would be wrong, okay? So we need to calculate essentially two transients. One transient is the transient that occurs during the integration time, that is when the switch is open, and the other one is the transient after closing the switch, okay? We shall actually calculate only one of them, the first one. So in order to calculate the transient, that is the discharging of the capacitor during the integration time, what we have to do is to calculate the time evolution of Vd, okay? So we have a capacitor with a constant current flowing into it with some initial condition on the voltage that is equal to Vd, okay? Let's go to the next page. Actually, the next page was already completed because we calculated the continuous mode. So this is instead the calculation of the transient of Vd in the storage mode, okay? So we start by considering that if the voltage across the capacitor changes by some quantity dVd, the amount of charge that enters the capacitor is some dq, and dq is given by the product of the variation in the voltage times the capacitance. Of course, you remember the PN junction in the reverse bias is a non-linear capacitor. So we must use the differential capacitance. And we already found the expression of the differential capacitance. It is given by some constant C0. And this constant is the value of the capacitance when the applied voltage is 0, that is at equilibrium of the PN junction. And this is divided by you remember, the square root of 1 minus the applied voltage divided by the built-in potential, okay? So the square root would be to 1/2, okay? You remember that the calculation related to the differential capacitance of the p-n junction was carried out considering the simple case of the abrupt junction, okay? But in real life, junctions are not abrupt. However, when we calculate the capacitance, for instance, of a p-n junction in which the substrate has a uniform doping and the upper zone has been obtained by diffusion, we find that the differential capacitance can be approximated with a similar expression in which, instead of having m equal to 2, we have m equal to some number larger than 2, like 3, for instance. For the diffuse capacitance, m would be equal to 3 instead of 2. So essentially, we write in a more general form the differential capacitance as C0 over 1 minus Vd over psi 0 to the power 1 over m. On the other hand, what is the relation between the variation of the charge and the current density? Of course, since we are considering this charge Q is a charge per unit area. And this differential capacitance, C, also is a differential capacitance per unit area. Okay, so the variation in the charge, by definition, is equal to the current times the elementary time during which we are considering this charge entering or exiting the junction. Okay, so we must consider the current per unit area, that is the current density. And we already know that the current density is some minus J, minus because it goes upward in the figure. And if you assume that this current is essentially due only to the optical generation, then minus J is a constant that we already calculated. It is Q times G sub S over K, okay? So what we do is very simple. We replace dQ with minus J dt. Of course, minus J is given, okay? And here we replace C with C0 divided by 1 minus Vd over psi 0 to the power 1 over m. So essentially, we have a differential equation whose unknown is the voltage drop across the junction with respect to time. Okay? So in order to integrate this equation, we change the variable because it is more convenient. We call the variable W. W is 1 minus Vd over psi 0. It is a non-dimensional quantity. So the equation to be solved becomes, it's a very easy differential equation. Minus J over C0, psi 0, these are constants, times dt is equal to minus W to the power minus 1 over m times dW, okay? Now, we put together all the constants into a time that we call tau 0. Okay, if you check, the capacitance times the voltage is a charge per unit area divided by a current per unit area. Of course, it gives you a time. So tau 0 is minus C0 psi 0 over J, and this is positive. And then we call alpha equal to 1 minus 1 over m. So in conclusion, the dependence of W on time is given by this relation. And of course, W0 is the value of W at time equal to 0. So it is 1 minus the applied bias V0 divided by psi 0. Okay. So the issue is that the initial voltage V0 is negative, and as time evolves, the voltage drop across the junction is less and less negative. So at any instant of time, VD will be still negative, but larger than V0. Okay? So what we do is we wait for some time, that is the integration period. Let's call it capital T sub E. So we let time evolve from 0 to this capital Ti in this equation, okay? And then we calculate the value of Vd at the end of the integration time. The values of the quantities are such that we can introduce some simplification by linearizing, as we shall see in a second. Typically, the integration time, capital T sub I, is much smaller than tau 0. The integration time, you remember, is in the range of a few milliseconds. Okay, so we can expand the right-hand side to first order, and then we replace the original variables, okay? So what we find is that the ratio between the integration time and tau 0 is the ratio of the capacitance when the applied voltage is V0 divided by C0. You remember C0 is the equilibrium value, so when the voltage is 0, okay? Times V0 minus Vi over psi 0. V0 is negative, Vi is less negative, so this fraction is negative. With the minus sign in front, it becomes positive, okay? Now we calculate the current in the load resistor, the current that we call IR. Obviously, it is equal to V0 minus Vi over R, because you remember right before closing the switch, beta has the same voltage as gamma, so VR is 0. When we close S, we bring alpha and consequently beta back to V0. So we impose a variation. Sorry, we bring alpha back to V0. So we impose a variation V0 minus Vi to beta, whereas gamma stays to ground. So the current at the time of closing the switch is V0 minus Vi over R. And then we replace all the quantities because we can extract V0 minus Vi from the first relation. So it is this one. And this is the current, okay? This current can be divided by the current of the generator. You remember the current gain of the storage mode operation with respect to the continuous mode operation is the ratio between IR divided by IG, but IG is the area of the diode times J. So when we do this, we find that the current gain is Ti over R times the area and times the capacitance at CV0. So we can use sensible values for these quantities. For instance, we take Ti equal to 1 millisecond, which is not very large. It could be larger, okay? We use 1 kilo ohm for the resistor and 1 picofarad for the capacitor. Of course, we must multiply the area because C in itself is a capacitance per unit area. So if we replace this number, what we find is a very large gain, like 1 million, okay? So it is much easier to detect this signal over the resistance, okay, than to detecting the current or the voltage drop in the continuous mode, okay? We mentioned that when we start you remember there is the integration time where the switch is open, okay? And then there is the sampling time when the switch is closed, okay? The sampling time is described by a different set of equations because the resistor is crossed by some current because the switch is closed, okay? So during this period of time, the sampling time, the current in the resistor is of course equal to the cross-sectional area of the device times the time derivative of the charge per unit area, okay? When we replace these quantities, we can write the current in the resistor as V0 minus Vd over R. And the variation with respect to time of the charge is, of course, the differential capacitance times the variation with respect to time of the voltage drop across the PN junction. This is a non-linear differential equation that can be solved. It's non-linear because C depends on Vd in a non-linear way, okay? It can be solved depending on the value of the exponent m. So it's relatively easy if the exponent is equal to 2 or 3, okay, that are the typical values of the exponent. But we shall not consider this calculation. We can observe another thing, that since we have linearized the relation that occurs between time and voltage during the integration time, we expect that in this approximation, the voltage Vd will be a linear function of time. And I have a figure. This figure, for the moment, is not in the collection, but will be posted later in the afternoon after the lesson is finished. So I have to change the video. there it is. So this page shows the evolution in time of the voltage across the p-n junction, of the voltage across the resistor, and the status of the switch. So if you look at the lower part of the figure, you see that we have integration times of length Ti. All of them are equal to each other, of course. And during them, the switch is open. And then the integration periods alternate with the sampling periods, T sub s, okay, in which we have the discharge of the accumulated charge of the p-n junction. If you look now at the upper diagram, you see that the voltage Vd is always negative, okay? Then at the beginning of the integration time, this voltage is negative and equal to V0. V0 is negative, okay? Then it becomes progressively less and less negative, but it stays negative anyhow. And it is described by a linear relation because of the linearization that we carried out, okay, which is very reasonable due to the quantities involved. So when we reach the end of the integration time, Vd has changed from V0 to some value, okay, and this value, of course, depends on the current produced by the generator, and in turn, this current depends on the illumination that exists during this integration time. At this point, we close the switch, we start the sampling time, and we have another transient in which the voltage across the p-n junction must go back to the original V0. Okay, this is why the sampling time must be long enough. Okay, otherwise this voltage would not have time to go back to the original value V0. Okay, then we start again an integration time, and the final value reached by Vd during the next integration time is not necessarily equal to the other case, because maybe during the second integration time, the illumination has changed, okay? If we are recording with a video camera, we are recording something, okay? This something may change, the illumination may change in time, okay? So it is still a straight line, but different from the other one, okay? And then we have another sampling time and so on, okay? If you look at the lower, intermediate graph, this intermediate graph is the voltage drop across the resistor, the load resistor. So when we are in the integration period, the switch is open, so there is no current flowing through the resistor. You remember, that is, the voltage drop will be 0. When we close the switch, we have a peak of current. In fact, you can see it. Of course, the peak of current depends on the value of VD reached during the integration time. So this peak is negative, but its modulus is smaller than the modulus of the next peak, because the next peak corresponds to a larger, that is less negative value of VD. Okay, so our signal is the succession of these peaks across the load resistor R. Okay, and as we commented yesterday, if you use this type of device to form an array of pixels for a video camera, and the period of the video camera, the period is Ti plus Ts, of course. Okay, so the signal has a period that is the sum of the integration time and the sampling time. Okay, if this period is smaller than the so-called retention period of the brain, okay, presenting static frames gives the illusion to the viewer of an image that is moving. So this is the principle on which, for instance, displays like TV displays or computer displays or whatever are based on. Sorry. Now we go back to the other image, to the other page. There it is. Now the question is, how do we realize the switch? There are two possible implementations. One possible implementation is to use for a switch another diode. The other diode is exactly another PN diode placed in parallel to the photodiode, okay? Of course, the diode that operates as a switch is protected from the radiation, so there is no optical generation in it, okay? Another property of the diode that is used as a switch is that its cross-sectional area is much smaller than the area of the photodiode. Why? Because when we switch a diode, we always have a rearranging of charge, okay? So there will be also some charge flowing to and fro between the switch diode and the photodiode. And we don't want that the charge of the switch diode pollutes the other charge. So the area of the switch diode is much smaller than the other one. And then we apply a generator, a voltage generator with pulses between point gamma and the lower and the N side of the switch diode, okay? So assume that the voltage generator that is in series to the switch diode is suddenly brought to a very negative value, okay? So gamma, as usual, is put to ground, is the reference voltage, okay? point delta goes to a very negative value, okay? So the N side of the switch diode goes to a very negative value, and the switch diode becomes biased in direct bias, okay? Alpha follows, because if D becomes very negative, alpha will have the voltage of delta plus the threshold of the diode, okay? So there will be a small difference in the electric potential between alpha and delta, so that alpha will also be negative, okay? If alpha is negative, then the photodiode is biased in the reversed condition, the reverse bias, okay? As long as we keep this operating condition, the loop is closed, because we have the voltage generator, then we have the switch diode that is forward biased, so the loop is closed. And then we have the photodiode, and in the photodiode there is the current generator, as you remember, that produces the current. Okay, so there is a current flowing through the circuit. Then at some point we bring the voltage generator from the very negative value of the voltage to 0. Okay, so all of a sudden point delta goes to voltage 0, whereas point alpha was negative. Okay, the switching diode has no time to rearrange the charge. Okay, so essentially the switch diode becomes a diode in which the N side is at 0 and the P side is with a negative voltage. So the switch diode is reverse biased, so it becomes an open circuit. Okay, so having the voltage to 0 is equivalent to having the switch open in the original picture of the circuit. When the switch is open, we have the integration time. So if you look at the diagram on the lower right part of the figure, the voltage generator alternates between very negative and 0. When it is very negative, we have the sampling time. When it is 0, we have the integration time, okay? Now, one question comes about. If you look at the switch diode, the switch diode has the P region on top, on the side where alpha is, okay? And this P region is shorted with the P region of the photodiode. So we have two P regions that are shorted together. So the question is, why should we keep them separated? Why don't we put them together? Okay. You simply may imagine that you seize the switch diode and drag it upwards and then to the left and push it into the photodiode. Okay. What do you get? Well, obviously, what you get is this. So on the left part, we still have the two devices separated, but the switch diode, instead of being drawn as a symbol, is drawn with the actual structure, okay? And then we bring its P region into the, and we merge its P region into the other region, okay? So if you do this, what you obtain is the structure that is shown on the right side of this figure. And of course, you obtain a transistor because you have the lower part is N, it's just the original N part of the photodiode. Then you have a P plus region that is plus plus, put it even more doped, okay? It is the lower part of the original switch diode that has gone into the transistor. Okay, so together they have a structure NPN. So it is just a bipolar transistor operated with the generator, and the gamma, delta, and beta points are in the same position as before. Nothing has changed in the external part of the circuit, okay? So of course we keep the P plus region that now has become the base of the NPN transistor. We keep it very large in order to have a large area exposed to the radiation. And also, we don't have any contact to the base. The base has no contact, of course. Okay, the base is floating. Okay, so this is the bipolar phototransistor. Okay, the bipolar phototransistor. Now we stop. We shall continue in 10 minutes to show the other possible implementation of the switch. We stop now. Okay, so let's continue by considering the other possible solution to the switch problem. Let me share the screen again. So this is the bipolar phototransistor that we already discussed. The other possibility for implementing the switch is, of course, using an MOS transistor. Okay. So in this case, we use for the switch an MOS transistor, and for reasons that will become clear in a second, instead of considering an N-channel transistor, we consider a P-channel transistor. Okay, it is clear that we are using a P-channel transistor because you see the arrow of the source points into the device. Okay, so this symbol is the symbol for the P-channel transistor. The P-channel transistor is dual to the N-channel transistor. So in order, when you have an N-channel transistor, in order to have the channel well formed, you apply that large positive bias to the gate. In this case, in order to have the channel well formed in the P-channel transistor, you must apply a large negative voltage to the gate. So you see that, again, the voltage generator here switches from a very negative value to 0. So when we have a very negative value, the channel of the MOS transistor is well formed and the transistor is active. So we have a connection between points alpha and delta, meaning that the switch is closed. When we have instead a voltage equal to 0 applied to the gate, this means that the transistor operates below threshold, so it is essentially off. And we do not have any connection between points alpha and delta, and in this case, we are in the integration period. So you can see on the right, small vt goes from very negative to 0 and back. When it is 0, we have the integration period. When it is very negative, we have the sampling period. Okay. Now the question is, why did we select for the switch a transistor of the P-type instead of a transistor of the N-type? We did so because the photodiode has the P-type on top. So also in this case, the source of the P-type transistor is a P region, okay, because the P-type transistor is dual with respect to the N-type transistor, okay. So the substrate here is of the N-type, and the drain and source regions are of the P-type. So this P-type connected to point alpha is actually shorted with the P-type of the P region of the photodiode. So again, we can think of merging the photodiode and the switching transistor together, okay? To do so, we must also preserve all the other connections. So you see that point delta is the drain of the transistor. It is connected to V0. And the gate of the transistor is connected to the other generator and to the voltage generator, and the lower contact of the latter is connected to gamma. Okay, so now we replace the structure of the p-channel transistor. It is here. It is still separated, but you see that the source region is of the p-type and it is connected to point alpha and is shorted with the p region of the photodiode. The gate contact goes to the generator. The drain contact goes to delta. Then we have gamma, and point beta is the substrate of both. Okay, point beta, we go up again. Point beta is the substrate of the photodiode, but somewhere here we also have the fourth contact of the transistor, that is the substrate of the transistor, that is the reference for the voltages. Okay, so this point beta is also connected to the bulk of the transistor. So we may think of merging not only this p region with the other p region, but we should also merge the two bottom contacts, this one, and correspondingly the substrate region of the transistor that is of the n-type with the n region of the photodiode. Okay, so these two n regions also go together, and finally what we get is the MOS phototransistor. Okay, when we put everything together, we obtain this structure. Okay, you see that all connections are respected. Okay, well, alpha has disappeared because alpha is the common point here that disappears when we put the two p regions together. So alpha disappears simply. Beta is here, is not indicated, but beta is here, is the bulk contact of the phototransistor, and gamma and delta are still there. Okay, so this is the MOS phototransistor, in which there is no contact on the source, and the source region is very extended, so we have a large area for the photons to enter the semiconductor. So what happens is that during the integration time, there is no channel. There is no channel here because the transistor is off. We have a 0 voltage on the gate. So simply the PN diode made of the PN junction of the source integrates the charge. When the integration period is finished, we put a very negative voltage on the gate. We create the P channel connecting source and drain, and we absorb the drain current through this contact, and then we read it on the resistor. Okay, so this is another implementation that is the MOS photo transistor, that is an evolution of the photocapacitor combined, of the photodiode combined with the transistor used as a switch. Before continuing with the optical sensors, we examine another possible application still in the optical field in a broader sense of the p-n junction. So we consider the solar cell. Let me find it. The solar cell is still a sensor. However, the application of it is not that of detecting the intensity of light at some position, but as you know very well, the aim is absorbing the energy. Okay. So the solar cell has the same structure as a photodiode. It is a p-n junction, very shallow, so we have the minimization of the electron hole pair generations in the neutral region of the p-type. The only difference is that we don't have a bias, okay? We simply attach the device to a load resistor. So this load resistor may be anything, may be an engine that we want to operate with the solar cell, or something that accumulates the energy or something else, okay? The issue is we don't have any generator, so we are not spending energy like we do, for instance, in the photodiode or in the phototransistor, okay? Because there we have generators applied from outside. Here we don't have any generator. And the purpose is to see whether this device is able to transfer energy into the load resistor, okay? So when we have some light impinging on the solar cell, since the solar cell is exactly as before, it is a photodiode, we know that the action of the external light is essentially that of placing a current generator in parallel to the cell, okay? What is the difference here? The difference is that when we have a photodiode, we know that we are applying a reverse bias because we have the external generator connected to it. So when we have an external generator that forces a condition of reverse bias, we know that the photodiode essentially behaves like a capacitor. And when we have, in addition, the illumination, we have a capacitor with a current generator in parallel. In this case, we do not have any external bias. So we don't know a priori whether the voltage that may appear at the contacts of the solar cell is positive or negative. We don't know yet. We'll calculate it, okay? But we don't know. So we cannot represent the p-n junction just as a capacitor. We must represent the p-n junction as a full diode, okay, ID. And then we place in parallel to it the current generator. So the equivalent circuit of the solar cell is made of the parallel of a diode and of a current generator. You also remember that the current of the current generator points upwards, okay? So we are sure that this generator will provide a current that goes bottom up. For the current through the diode, we don't know yet. So we simply call it ID, and that's it. Then if you look at the two contacts of the diode, okay, the diode in parallel to the current generator is a bipole, okay? So all the things that are on the left of the vertical dashed line constitute a bipole for which we assume provisionally that the voltage V has the orientation indicated by the arrow and the current I has the orientation indicated by the arrow, okay? Now, we hope that this bipole made of the solar cell, made of the PN junction in parallel to the generator will be able to provide energy to the resistor, okay? You remember that the electric power on a bipole is the product of the voltage V times the current I, okay? And what we want is that the power goes from left to right. So the power must cross the vertical dashed line going from the solar cell into the resistance, okay? But this power is calculated as the product V times I, so it must be negative. So either V or I must be negative in order to have the power going from left to right. Obviously, this is the only possibility for the power because in no way there could be any power going from right to left because this will be against thermodynamics. We would produce energy from nothing, okay, if the power went from right to left, okay? But we shall calculate it and we eventually shall see that the power goes from left to right as it should be, okay? The calculations are a little bit more complicated with respect to the photodiode because we do not know a priori what happens. Okay, so we must perform a full calculation solving the semiconductor model. Okay. Let me zoom in just for a second. So this is the structure of the solar cell, just a photodiode. We use the same symbols. So we place the origin in the position O minus, that is at the edge of the space charge region in the p-type. The extension of the neutral region of the p-type is called S. So the position of the outer edge of the device is at minus S. So the neutral region of p-type is between minus x and 0, minus s and 0. We assume the weak injection condition, so we can linearize the minority chiral net recombination function u. Then we assume that the radiation is monochromatic. Of course, this is not true. Okay, a solar cell absorbs different frequencies from the radiation. Okay, but for the moment we take a monochromatic radiation, and then after the calculations will be completed, we shall sum up the contributions of the different monochromatic components. So for the moment, we consider that the absorption coefficient K is just one value. It does not depend on frequency because there is only one frequency, okay? Then the other symbols are as usual. We call GS equal to G0 exponential of minus KS, as we did in the photodiode, okay? So the illumination can be written as GS exponential of minus KX. Then we simply solve the PN junction again. So at this point, we must solve completely the PN junction with only one difference with respect to the standard case of the PN junction. That is, we have also the optical generation. So the continuity equation for the minority chirals in the P region, that is the upper part of the device, is in steady state the derivative of Jn equal to Qu minus Qg. So the new thing is minus Qg. Okay. We keep the assumption that the contribution to the minority current is essentially diffusive. So Jn is practically equal to the diffusive part, Qdn derivative with respect to x of n or n minus np0. So at this point, we have a differential equation in which you can see the first two terms are those of the usual differential equation that we already solved in the PN junction without illumination. In addition to that, we have the contribution to the optical generation. So what is the difference between this equation and the equation for the standard PN junction? The difference is that in the case of the PN junction, the equation is homogeneous, and in this case, it is non-homogeneous. Okay, so we have an extra term. We make an hypothesis, which will be explained later. The hypothesis is that the inverse of K, of course, K is the inverse of a length. So the inverse of K is a length. We must impose that 1 over K is different from the diffusion length of the electrons. You remember the diffusion length is the square root of the relaxation time, the lifetime of the minority chirals times the diffusion coefficient of the minority chirals. Okay, why should we impose this constraint? Because, as we shall see in a minute, if 1 over K is equal to Ln, the equation becomes again homogeneous. Okay, we shall see it in a minute. Now, how do we solve a linear equation of the second order that is non-homogeneous? We simply, as you remember from elementary calculus, we take the solution of the homogeneous equation. And the solution of the homogeneous equation, of course, has two constants in it. One is an and the other is bn. Okay, and these two constants are found by imposing the boundary conditions. Okay, so when we have an equation that is non-homogeneous, we add to the non-homogeneous solution a tentative solution for the non-homogeneous case. We just look for any function able to solve the equation, okay? And we shall see in a minute that this form Cn equal to exponential of minus kx is a possible solution of the non-homogeneous equation, okay? This form of the solution also explains why we should take 1 over k different from ln. Because if 1 over k is equal to ln, this term with Cn becomes identical to the term with an. So we put them together and we are left only with the homogeneous solution, okay? So in that very special case, the solution is only homogeneous, okay? So we exclude the special case. Remember that the two parameters to be found from the boundary conditions are an and bn. Cn is not found from the boundary conditions, okay? Cn is simply found by imposing that this term, Cn times the exponential of minus kx, solves the equation. So we simply plug this one as a possible solution. So we replace these two n minus np0, and we calculate the result. So the second derivative, okay, is equal to k squared times the constant times this function, okay? The second derivative of np0. And we replace it here, okay? And then we have again n minus np0 over ln squared, and this is it, okay? So this relation must be fulfilled, okay? So we simply take the second derivative from the upper equation, replace it, and find the value of Cn, okay? We find a relation involving Cn and other quantities. So, but again, I repeat, by forcing this term to solve the equation, we find the parameter Cn. This parameter has a value that is shown here. Cn is equal to tau n gs divided by 1 minus k squared ln squared. So you see the constraint. If the constraint is not fulfilled, okay, there would be no Cn because the denominator here would be 0. Okay. Now we have found Cn, we need finding an and bn, but we do it as usual considering the boundary conditions of the Pn junction. Okay. So number one, we impose the boundary condition at 0. You remember 0 corresponds to O minus, and O minus is the edge of the space charge region on the p side. So the value of the electron concentration at that point is given by the Schottky Shockley boundary condition at O minus. And this boundary condition, as you remember, is n equal to np0 exponential of qv over kt. So by replacing this, we find a relation in which we have the usual term f, that is the exponential of qv over kt minus 1. We have the two constants to be found, an and bn, and cn is given. Cn is already calculated, okay? So if we go back to the figure, we have solved the minority carrier equation in the region, in the neutral region of the p-type from minus s to 0. And then we have imposed the boundary condition at 0. Now we must impose the boundary condition at minus s, but here we have a difference with respect to the standard analysis of the p-n junction, because in the p-n junction, you remember the two boundaries are taken at infinity. But in this case, the junction is shallow. It is very shallow, so we cannot take minus s at minus infinity, okay? Minus s is actually very close to the origin. So in the solar cell, we do not have anymore an asymptotic condition. We have a condition at a finite distance from the origin, but this is no big deal. We simply impose that on the contact, that is in the position x equal to minus s, we have that the concentration of the electrons is equal to the equilibrium value. So we take the condition of equilibrium, but at a finite distance from the origin. So we have this relation, okay? So we have two relations. One is np0f equal to an plus bn plus cn plus cn. The other is this one, okay? Actually, we can exploit the fact that the junction is very shallow by simplifying somewhat the exponentials, because actually s is typically much smaller than the diffusion length. And also s is typically much smaller than 1 over k. So the exponents here are small. We can linearize the exponentials to find that exponential of minus s over ln is practically equal to 1 minus s over ln. The one with the plus has 1 plus s over ln, and the other one has 1 plus ks, okay? So this is a small simplification that we can introduce, okay? After this, we manipulate these two relations because we want to extract an and bn. These calculations are elementary, so I'm not going to too deep into them. At some point, you remember, we calculate Jn at O minus, because we need it in the standard theory of the p-n junction. Jn of O minus is simply Jn calculated at x equal to 0. So the expression of Jn is here. You remember Jn is q dn, the derivative of n. So from there we calculate Jn. we set x equal to 0 everywhere because we need Jn of O minus. So from this line, we obtain this other line, okay? At this point, we replace the values of An, Bn, and Cn, and amazingly, we find a very simple relation. So Jn at O minus is almost equal to the standard expression of Jn of O minus of the p-n junction, with only one exception that you remember. In the standard p-n junction, in the denominator we would have ln, okay? In this case we have s, so there is a little change in the formula, okay? So Jn of O minus is almost the same as for the standard p-n junction, okay? We just replace ln with s. Now we go to the other side. We do it in the usual way. What we do is we take the continuity equation for the electrons and we integrate it over the space charge region, so that we have Jn of O plus is E minus Jn of O minus is equal to the integral of Qu. This is, as you remember well, nothing else than the recombination current. Okay, so Ju is something that we know already. Then we have Jg. Jg is the integral of Qg. This integral is, of course, equal to Qgs over K. Then we have the exponential in O minus, but O minus is 0, so the exponential gives you a 1. Minus the exponential of minus k x of O plus, okay? And we simplify this because, as we did already in the photodiode, the dopant of the N zone, the lower part of the solar cell, that doping is very small, okay? The concentration is small. So, and this is so because we can obtain in this way a very large value of the extension of the space charge region, so we can collect all photons, okay? So x of O plus is large, so that kx of O plus is a larger number, so the exponential is negligible. So also in this case, we have that the effect of the photons is just that of a current generator whose current density is Qgs over K, okay? Now we go to the other side, okay? We have to solve, as typical of the p-n junction, we have to solve in the neutral region of the n-type. But in the neutral region of the n-type, we can introduce simplifications because the edge of this region, you remember the edge is x of O plus, is very deep because the extension of the space charge region is large, okay? So since the photon flux decays exponentially as the radiation penetrates into the material, practically when we are at O plus or deeper than O plus, there are no photons left. All photons are practically have been absorbed, okay? So we simply, in the neutral region of the n-type, we neglect G, the optical generation. But in doing so, we are left with an equation that is exactly the standard equation of the N region in a p-n junction. In this case, we have that there are only two constants in the differential equation, AP and PB. We do have an asymptotic condition. So this theory is exactly identical to that of the standard p-n junction. And what we eventually find is that Jp at O plus is equal to the standard expression Q dp pn0 over Lp times F. At this point, we calculate the total current density using the usual trick. We start with Jp and Jn at the same position, O plus. Then Jp of O plus is of the minority Carrier type, and we keep it. Jn of O plus is like Jn of O minus plus Ju minus Jg. Okay. We put all the ingredients together. We define a modified saturation current density of the solar cell. And the expression, you see, is almost the same as for the p-n junction, or the traditional p-n junction. The only difference that we already noted is that instead of having Lp here, we have S, okay? So we call this Js prime, just to remember that it is different. So globally, the equation of the p-n junction can be written as Js prime F. F, you remember, is exponential of QV over KT minus 1, plus the recombination current density minus Jg. And the quantity in parentheses is just the equation of a diode. So we call it JD. Okay, so this analysis shows that without knowing, we don't know yet whether the bias is positive or negative, okay? But from the analysis, we understand that it is correct to describe the solar cell as the parallel of a diode and of a current generator, and since we had a minus sign in the current of the current generator, this current should go upward. Okay, so this is the correct equivalent circuit of the solar cell, and we don't know yet whether V is positive or negative. We don't know. We must calculate it now. Okay, so in order to calculate the actual voltage and current of the solar cell, we use the standard analysis of the circuit theory. We do it graphically, okay? We take the IV curve of the bipole that is on the left of the vertical dashed line. Then we draw the load characteristic, that is a straight line, of course, okay? And we take the intersection of the load characteristic with the bipole characteristic. And this intersection, as you remember well, provides the working point of the solar cell. So it provides the true value of the voltage and current, voltage V and current I of the solar cell. Before doing that, considering that we have little time before the completion of the hour, we now remember that the radiation is non-monochromatic. The radiation has a spectrum, which means that the generation at the origin, remember G0 is the point where the radiation penetrates the solar cell immediately inside, okay? So G0 depends on the frequency of the radiation, but also the absorption coefficient depends on the radiation, okay? But this is an easy matter because instead of taking a single expression for the generation term, we take the elementary generation at frequency Ni. So we consider small gs such that small gs times d Ni is the number of generations per unit volume and time at frequency Ni. Then we multiply this by the absorption term, exponential of minus kx, and then we integrate over the spectrum of the radiation from 0 to infinity, okay? The same thing we have to do for this coefficient here, okay? So we are simply doing a superposition. If we started with these expressions in the integral, instead of finding the expression for capital Cn, we would find an expression for some small cn, that is this one, equal to tau n small gs 1 minus k squared ln squared. So nothing would really change, okay? Now it is late, so we stop for 10 minutes and this is an easy part. We can complete it in a few minutes when we restart in 10 minutes. Okay. So we resume this part. We were just considering the case in which the radiation has a spectrum. There are very few differences. So, that is, instead of using capital G, S, and capital C, N, we use integrals involving them. So at the very end, the current density of the generator due to the optical generation is, instead of being Q capital G S over K, is Q times the integral of small g S over K integrated over the frequency. All the rest stays the same. So at the very end, the current density, as before, can be written as the expression of the current density of a diode having a modified saturation current density minus the current density of the optical generation. Given that, we of course go from the current density to the current by multiplying by the cross-sectional area of the device. So we have the current is ID minus IG. And in turn, ID is the expression of the current of a PN junction, IS prime exponential of QV over KT minus 1 plus IU. At this very moment, we don't know yet whether V is a positive or negative bias. This theory is fully general, but we can define some interesting points of the characteristic. You see that since the current due to the generator is a constant, the IV curve of the solar cell is simply equal to the standard characteristic of a diode shifted by a constant value. Okay, the fundamental expression is I equal to ID minus IG. ID is the characteristic of a diode. We simply shift it by a constant. I think there is a figure next. There it is. So if you look at the left side of this page, you see that this line here is the IV curve of the solar cell. It is exactly equal to the IV curve of a diode shifted below, so it does not cross the origin anymore, okay? Shifted below by the constant value IG. So we define 2 points, and these 2 points are the points in which V is 0. We call it ISC because it is the short circuit current, because V is 0. And of course, but we shall see it in a second with the calculation, it is equal to minus IG because it is shifted below by IG. The other important point here is the point in which the characteristic intersects the horizontal axis. And of course, this is for the case in which I, the current, is equal to 0. So this is called VOC. That is the open circuit value of the voltage. Okay. When we want to calculate the working point, we can do it graphically, so that we can consider the intersect between the IV curve of the solar cell and the load characteristic. The load characteristic is, of course, I do not rotate the figure because it is 1 second. It is the load characteristic of this resistance. So it is the relation between V and I of this resistance. But you see, I is oriented in this direction, okay? So the load characteristic is I equal to minus V over R, okay? So the load characteristic is a straight line with a negative slope, this one. So the intercept here is the working point. And you see immediately that the working point occurs or corresponds to a positive value of the voltage and to a negative value of the current. What does it mean? It means that, we go back to the other figure, it means that since the actual value of V is positive, the solar cell works in the forward bias condition. Okay, so it self-polarizes due to the current of generator IG. Okay, so V is positive and I is negative. You remember from the intersection, I is the negative. So the actual current here goes from left to right. And this, of course, means that the power V times I goes from left to right. So it is the solar cell that gives energy to the load R. Okay? These things are also shown in some easy calculation that follows. So you remember we defined the short circuit current as the current at V equal to 0. Okay, so it is IU minus IG, and if we have enough optical generations, IG dominates, so it is practically equal to minus IG. The open circuit voltage is the voltage such that I is 0. And this can easily be calculated by inverting the characteristic. Okay. For any voltage between 0 and the open circuit that are positive, the current is negative. And due to the form of the load, we have that, as you remember, the working point has a positive voltage and a negative current, so that the power goes from left to right. Given that, we may try to improve the description by observing that for a given working point, the power provided by the solar cell to the load resistor is the product VI, that is the area of the rectangle indicated in the figure. So this area in modulus has the power that the solar cell gives to the load. So we may think, for a given solar cell, we may think of adapting the value of the load resistance in order to maximize the power provided by the solar cell. How can we do it? Well, it is very simple. If you change the value of this resistance, the load line rotates around the origin. Okay, so this point changes up and down. So we simply seek for the position of the intercept that makes the area equal to a maximum. Okay, this can be easily done by calculation. Here, the power is I times V. So in order to maximize the power, we simply take the derivative of the power with respect to V and put it equal to 0. Okay? So since the power is I times V, the derivative of the power with respect to V is I plus V, derivative of I with respect to V. And this derivative can be calculated from the characteristic. Okay, so we impose that dP over dV is equal to 0. And we find the value of the voltage that corresponds to the maximum power. We call it VMP, V of maximum power. If we, in practice, do the calculation, we find that the V of maximum power is near the threshold of the PN junction. So with standard structures of the PN junction, the voltage of maximum power is about half a volt. Then we replace the V of maximum power into the characteristic of the solar cell. So we find the current of maximum power. And after that, the ratio of the V of maximum power over the current of maximum power with the minus, because the current is negative, provides the load that we should use in order to obtain the maximum power. Okay, so we assume from now on that we have adapted the load resistor in order to achieve the maximum power of the cell. Then we consider some typical parameters that are useful to characterize the solar cell. One parameter is called the fill factor. The fill factor is immediately understood from the figure. The fill factor is the ratio between the area of the rectangle and the area subtended by this portion of the curve. So you take the curve with voltages going from 0 to the open circuit voltage, okay? Calculate the portion of the area that is subtended under this curve. Of course, it is negative, and then you take the area of the rectangle and you calculate the ratio. This is called the fill factor. It is not an efficiency. It is not an efficiency. It is another thing, okay? The efficiency of the cell is another thing, and it is defined in a very obvious way. For simplicity, we consider the power per unit area, okay? So the efficiency eta of the solar cell is the ratio between the power per unit area produced by the cell and the power per unit area entering the cell. So the power that is produced by the cell is the modulus of V maximum power times I maximum power divided by the area of the cross-section of the cell. The power per unit area that enters the cell is something that we don't know yet, and we indicate it as dP in ds, okay, just the power entering the cell per unit area, okay. Anyhow, we can calculate the efficiency of a solar cell, and it is convenient to express the efficiency as the product of two efficiency. One is called eta prime and the other is called eta double prime, okay? Eta double prime is essentially due to aspects that are related to, for instance, the reflection of the radiation from the external surface of the cell. When there is a radiation impinging on the solar cell, part of it is reflected, so that is completely lost. Okay, those photons are reflected, they do not enter the cell, so they do not produce any optical generation. Another loss of efficiency is due to the fact that some electron-hole pairs, after being generated, they recombine. For instance, those that recombine in the neutral zone in the upper layers of the solar cell. Then we have a loss of efficiency that we shall discuss better with the figure, so we postpone this discussion. They are due to the so-called lateral resistances of the semiconductor and of the series resistance of the contacts. Okay, we shall come back to this later. Okay, then we have eta prime. Eta prime is the part of the factor of the total efficiency that is due essentially to the interaction of the radiation with the semiconductor. For instance, not all photons are able to produce an electron-hole pair. For instance, photons that have small frequency, so that the energy associated to them is smaller than the semiconductor gap, they of course cannot produce any optical generation. So those photons are lost. Some other photons do interact with the electrons, but they may interact with electrons that are already in the conduction band. So they increase their energy, but they do not contribute to their number because the electron is already in the conduction band. Some other photons may interact with nuclei, so they are also lost. Okay. So all these factors combined together decrease the efficiency of the solar cell. There is another effect that when the solar cell operates, of course, it is exposed to the solar radiation. So the solar cell heats up. It becomes warmer or hotter. Okay, depends. And when that happens, the efficiency decreases. Okay, the increase in temperature redistribute the carriers, and we have a decrease in the efficiency. Some cells may become very hot because in some cases people use mirrors to concentrate the radiation onto the cells. So cell may become really hot. Okay, so there are values in the table shown here in which there is the typical efficiency eta prime for silicon and gallium arsenide at 20 and 100 degrees centigrade. And you can see that eta prime halves going from 20 to 100 degrees. For silicon, it goes from 0.22 to 0.11. And for gallium arsenide, from 0.28 to 0.14. This is for eta prime. If you multiply by eta prime prime, then you obtain an even more pronounced decrease in the efficiency. So solar cells are not very efficient. These data are a little bit old. Modern cells have different combination of band gaps in order to be able to absorb more photons, a larger quota of the spectrum of the radiation. So modern figures are larger than this, but not that large. Okay. The other point is, given the efficiency, how much power is available? So how much power is coming in from the sun? This is another question, okay? So it is very easy to calculate the power that comes from the sun. Despite all evidence, it is a very easy calculation. Because consider the system made of the sun and the earth, okay? So the sun can be thought of as a uniform sphere with a radius equal to some value Rs, okay? And the energy that is provided by the sun spreads uniformly in space from the sphere, from the spherical surface of the sun into larger spheres until it reaches the Earth, okay? Assume that the orbit of the Earth is perfectly circular with a radius equal to r0, okay? So the same energy that is emitted by the sun on a sphere of radius rs spreads in space, and when it reaches the Earth, it is spread over a larger sphere of radius r0. So the surface of the sun is proportional to rs squared. The surface of the sphere associated to the radius of the Earth is r0 squared. So the power emitted by the sun when it reaches the position of the Earth decreases by the ratio rs squared over r0 squared. Okay, so we can immediately find the decrease in the power emitted by the sun. So the question is, how much power is emitted by the sun? And this is also easy because we can consider the sun as a black body of the type investigated by thermodynamics. Okay. And if you have a black body that emits power, there is a general law of thermodynamics that states that this power is proportional to the fourth power of the temperature of the emitting black body. Okay. So we can do a very simple calculation. Let's call dP in over ds star the power per unit surface that reaches the external edge of the atmosphere of the Earth, normal to it. So in the direction that goes straight from the sun to the Earth, but still on the outer edge of the atmosphere. So we do not include for the moment the absorption by the atmosphere, okay? This power is, of course, equal to the energy per unit time. This is the energy per unit time that impinges on the external edge of the atmosphere. Of course, due to the reasoning that we have just completed earlier in the considering the figure, okay, the energy arriving on the edge of the Earth's atmosphere is equal to the energy emitted by the sun per unit time and surface times the ratio of the two radii squared. Rs is the radius of the sun, R0 is the radius of the orbit of the Earth, okay? This is purely a formal set of steps. Now we assume that the sun can be described as a black body, which is practically true, okay? So the energy per unit time and surface is equal by the Stefan law is proportional to the fourth power of the temperature of the surface of the sun, Ts. Ts is the temperature of the surface of the sun. And there is a constant here that is called the Stefan-Boltzmann constant, okay? in this formula, there could be a mistake. So probably this factor 4 is not there, but also the ratio R0 over Rs is not 435, it is 1/2. So the 1/2 mistake in this ratio compensates the factor 4. So the conclusion is correct, okay? So if you simply plug in the temperature of the surface of the sun, that is 5,800 degrees Kelvin, okay, this is the temperature of the surface of the sun. What one obtains is that the power impinging per unit area on the edge, on the external edge of the atmosphere in the normal direction is 135 milliwatt per square centimeter. This is the so-called solar constant, okay? And this is the maximum power that we can achieve from the sun, nothing more, okay? Actually, what we achieve is much less because, number one, in the majority of locations on Earth, the angle of incidence is not 90 degrees, it's not normal, it's larger angle, okay? So we must account for the sine of the angle, okay? And the other factor is that the atmosphere absorbs very much. So there are frequencies in which there is a strong absorption, other frequencies where there is not a very strong absorption. In any case, the actual power per unit area is quite smaller than the solar constant, okay? And then we must multiply this by the efficiency, okay? So solar cells are very useful for some applications, typically of when there is little power necessary, okay? But if one wants to run an industrial system, I doubt that solar cells are the solution. Another issue is I left behind the discussion. Remember when we were talking about eta double prime, okay, we were talking about lateral resistance in the semiconductor and series resistance of the contacts. So when you look at the solar cell from the top side, typically you see something like this, okay? The black lines are the upper contact. Of course, the bottom contact is a full metallization of the bottom size of the cell, okay? Why is it has this form? The reason is that, consider, for instance, an electron-hole pair that is generated somewhere here in between, okay? You remember holes and electrons are separated in the space charge region. One current travels up and the other travels down. So the one that travels up must reach the surface of the solar cell, and then it must reach the contact, okay? So a solar cell may be a very large device, okay? So this, assume it is an electron, this electron must travel around until it reaches a contact. So the semiconductor has a series resistance, okay? So there is the effect of a series resistance that opposes the motion of the carrier when the carrier travels along the surface to reach the contact. Of course, we cannot fill up all the upper side of the cell with the contact, otherwise most of the radiation would be reflected. So we must leave as much as possible the upper surface of the cell bare in order to have the majority of the photons entering the semiconductor, okay? So the contacts should not be too large, okay? But they should be able to reach, to branch around in order to be reached easily by the electrons or holes. Also, one may think that we could design the contacts in order to have the contacts very thin, so they occupy the minimum amount of area possible, okay? But of course, if the contacts are very thin, they are very resistive, okay? So again, by making the contacts very thin, we add another contribution to the series resistance, which of course is dangerous for the functioning of the cell, okay? So we have opposite constraints. The contacts should not be too large because they occupy too much area. They should not be too thin because otherwise they would have a series resistance, an excessive series resistance. And they should also branch as much as possible over the area in order to be reachable easily from any position on the surface of the semiconductor. So the upper contacts of the solar cells look easy, look very simple. Actually, the design of the contacts of the solar cell is a complicated optimization problem. So designing these contacts is an art of optimization, okay? I think this is it. Yes, for the solar cells. We have only a few minutes left, so we can start describing another sensing device. Okay, we just give a description, a qualitative description of this device, that is the MOS photocapacitor, okay? The MOS photocapacitor is a very simple device. Look at the upper part of the page. We have the MOS capacitor, the standard MOS capacitor. And assume that we bias the MOS capacitor by applying a voltage to the gate such that the MOS capacitor goes into the strong inversion condition, okay? However, the applied voltage is a pulse. So initially, the MOS capacitor is in the flat band condition. So you remember the electric potential is uniform everywhere, and there is no net charge anywhere in the semiconductor. Then, from the condition of flat band, we apply a pulse that brings the voltage applied to the semiconductor to the strong inversion situation if we wait for enough time to the strong inversion situation to establish, okay? But this is a dynamic situation. We apply a pulse. At the time of application of the pulse, consider the example in the figure where we have a p-type substrate. We apply a large positive voltage to the gate. So this positive voltage, as you remember, pushes away the holes away from the surface, okay? But we don't have yet the inverted layer because the inverted layer takes time to form. The formation of the inverted layer is not immediate, okay? What is almost immediate is the formation of the depleted region, okay? So from the dynamic point of view, when we apply the large positive voltage, we have the instantaneous formation of the depleted region in the semiconductor with no inverted layer, okay? Then we keep the large positive voltage for some time, okay? If there is no light impinging on the device, the only phenomenon that occurs in the depleted region is the generation of electron hole pairs because of the thermal generation, okay? So we have a thermal generation that if the material is good, so that the lifetimes of the carriers are high, the thermal generation is slow. But if we wait for long enough, at the very end, we obtain the inversion layer due only to the thermal generation. Assume instead the case in which we also have photons coming in, okay? And that the number of photons is relatively large. So after the application of the pulse, we obtain the depleted region, the space charge region of the device, and we have at the same time generations due to thermal reasons and generation due to the photons. And if there are enough photons and if the lifetime of the thermal generation is long, we may also expect that the number of electron hole pairs generated by the photons is dominant, okay? So after some time, and of course this some time is the integration time, after the integration time has elapsed, we do have a layer of electrons at the surface, but the majority of these electrons have been produced by the optical generations. If you look at the figure, you see that as usual, when you have an electron hole pair, since we have applied a positive voltage on the gate, the electron is attracted to the gate, goes up and stops at the surface, giving a contribution to the inversion layer. Whereas the hole is pushed into the substrate, into the neutral region of the substrate, okay? So the issue is, if the semiconductor is good enough and the radiation is sufficiently strong, we succeed in forming a layer of electrons almost entirely due to the optical generation. So we have a charge that is proportional more or less to the number of photons that have arrived in the semiconductor. At this point, we must be able to detect this charge, and in this way we relate the amount of charge to the amount of photons arrived on the semiconductor during the integration time. So we have we transform the optical signal into an electrical signal. We don't have time to do this. We shall continue with the photocapacitor, which is a very, very important device because, as you may immediately understand, photocapacitors are simple devices. They are very simple, so they are easy to manufacture. So they have been very successful for the fabrication of optical sensors. Okay, we shall continue on Tuesday. For the moment, we stop here. There is 1 minute, so if you have questions, please ask them.